So, Good afternoon, everyone. My name is Jayansh Sharma, and I'm from the Indian Institute of Information Technology. Today, under the mentorship of Dr. Rituparna, I am excited to present our research titled Beyond Borders, Empowering Multilingual Forms with Generative AI using MarianMT and T5 models. So, starting with the introduction, our paper explores the integration of MarianMT and T5 models to overcome language barriers in multilingual forms. The main focus is on leveraging generative AI for real-time and accurate translations. This study highlights the advantages of these models in enhancing user accessibility and cultural sensitivity, and by improving real-time translation capabilities, we aim to enhance user experience and cultural understanding. To provide some background, natural language processing or NLP enables computer to understand and generate human language by processing text and speech data. Core techniques in NLP include algorithm for text analysis such as tokenization, part of speech tagging, and name entity recognition, that is NER. With advancements like transformer models such as BERT and GPT, NLP has significantly improved language tasks and is integral to generative AI for creating human-like text and enhancing multilingual translations. Now, what is generative AI and its NLP application? Generative AI refers to a type of artificial intelligence designed to create new content such as text, images, or audio that resembles human created data. In relation to NLP, generative AI utilizes it to understand, generate, and translate human language, enabling sophisticated interactions and translations. So coming to MarianMT model of generative AI, it is a multilingual neural machine translation model designed to handle a wide range of language pairs. Built on the transformer architecture, it provides high quality translation across many languages. MarianMT is basically pre-trained on large multilingual corpora, making it ready for immediate use without fine tuning. Its flexibility and efficiency make it ideal for tasks requiring robust out-of-the-box translation capabilities. So now let's delve into the architecture of the MarianMT model, which is specifically designed for neural machine translation. The architecture comprises several key components that work together to ensure uh, ensure high quality translations. That is like encoder, for example. The encoder handles the input text by capturing the context and relationship between words. It uses self-attention to let each word pay attention to every other word in the sentence, no matter how far apart they are. This helps to understand the context better. The feed-forward network then refines these representations to ensure accurate context capture. Then next is decoder. The decoder creates the translated text using self-attention and encoder-decoder attention. Self-attention helps it consider all previously generated words for coherence. Encoder decoder attention lets the decoder focus on relevant parts of the input text provided by the encoder, ensuring the translations matches the original meaning. Cross attention Then the cross attention aligns the source and target languages by allowing the decoder to focus on the relevant parts of the source text. This alignment is crucial for the maintaining the translation's semantic integrity. Then there is positional encoding. Since the model doesn't inherently know word order, positional encoding is added to the input embeddings. This provides information about each word's position in the sequence, helping the model preserve the meaning and structure of the text. Now the comparison, like MarianMT differs from the models like BERT and GPT. BERT is basically bidirectional and designed for understanding text, not for generating tasks. GPT is unidirectional and focused on generating text, making it less suitable for translation. MarianMT, however, combines bidirectional context understanding with a focus on translation, making it highly effective for accurate translations. This diagram highlights the NMT framework encoder decoder structure. MarianMT uses this architecture enhanced with advanced transform mechanism for multilingual translations. Now, looking at the flow and connections with the MarianMT model, the first one is the input layer. This layer takes the source text and initiates the translation process. It converts the text into embeddings that the model can process. Then there is encoder layer. Each encoder layer comprises self-attention and feed-forward networks. Information flows through multiple stack layers, each refining the representation of the input text. Now there is decoder layers. The decoder layers also features self-attention and encoder-decoder attention mechanism. They generate accurate translations by applying feed-forward network and layer normalization, ensuring each word in the output is contextually appropriate. Then there is output layer. The final layer converts the representation from the decoder into the target language text. This involves mapping the process embeddings back to the word in the target language. So why we have chosen MarianMT is because it uses advanced transformer architecture to deliver high quality translations across many languages with a single pre-trained model. This offers a greater efficiency and scalability compared to traditional language pair specific models. By experimenting with MarianMT, we can evaluate its performance against existing models, explore its effectiveness in diverse languages, context, and potentially uncover improvements for multilingual translation tasks. Now, next model we used is the T5 or the text-to-text transfer transformer model developed by the researchers at Google AI, which treats every NLP problem as a text-to-text problem. It features a unified framework that converts all tasks into a text-to-text format, such as translating, summarizing, and answering questions. T5 scalable architecture and versatility make it capable of handling a wide range of NLP tasks with state-of-art performance. Now, T5 also follows the encoder-decoder structure, but there is some distinct features. Like the encoder has input embeddings, means the encoder converts input tokens into dense vectors that the model can process. Then there is positional encoding. Similar to the MarianMT, T5 uses positional encoding to add the information about the order of words in the sequence. Then there is multi-head attention. This mechanism allows the encoder to focus on different parts of the input text, simultaneously capturing various aspects of the text. Then there is feed-forward network, that is nonlinear transformations are applied to the output of the attention mechanism to refine the representations basically. And there is decoder also. Then self-attention mechanism, there is a self-attention mechanism in the decoder section. The decoder attends to all the words in the target sequence to generate contextually coherent output. And then the encoder decoder attention mechanism allows the decoder to use the information from the encoder to generate accurate translations. Then there is feed forward network similar to the encoder. The decoder applies nonlinear transformation to refine the output. Next is the attention mechanism. Uh, it has the scale dot product attention computes that computes attention scores, guiding the model on which parts of the input text to focus. And there is multi-heading attention that enhances this by using multiple attention heads to capture different types of information, improving the model's understanding and generation capabilities basically. So for stabilization and faster training, layer normalization is also applied before feed forward and attention components. Feed forward networks then process the attention outputs with nonlinear transformations to create final representation. Additionally, T5 also uses a simplified scheme for positional encoding compared to other models, helping the model to understand the order of words in a sequence. So now why we have chosen T5 for our research target is because T5 unified text-to-text framework excels in translation, summarization, and text generation. It is trained on diverse data sets basically, and handling multiple languages with the consistent high quality results, etc. Its seamless integration into platform automates translation and enhances multilingual user interfaces, making it a robust choice for multilingual conversions. Now let's discuss the Hugging Face Transformer library, which includes both MarianMT and T5 models we've covered till now. This is an open source project which makes it incredibly easy to access state-of-the-art NLP models. It supports a variety of models, including MarianMT, T5, BERT, and GPT, which allows researchers and developers to implement these models with minimal effort. One of the key benefit of this library is that it includes pre-trained model, which can save a lot of time and resources. Additionally, it provides tools for fine-tuning these models, making it an invaluable resource for a wide range of NLP projects. Whether we are working on translation, text generation, or understanding the Hugging Face Transformer library, the Hugging Face Transformer library has the tools we need to get started quickly and effectively, basically. Now let's look at the steps involved in implementation of T5 model for multilingual forms. First, we import the necessary libraries and define some sample health data to work with. Next, we retrieve the ISO 639-1 language codes and name to create a mapping dictionary basically for 20 languages only. This is essential for language mapping step. We then prompt the user to input their target language code or name, and if necessary, convert it to ensure that it matches our mapping. Once we have the language selected, we initialize the MarianMT model and tokenizers for the specific language. Finally, we iterate through the health data, translating each entry and display the translated text. This process ensures that our health data is accurately translated into the desired language. This is the example how we implemented the code explained in the previous slide. Now into the implementation of the T5 model. First, we install the necessary libraries and import the T5 model and tokenizer. We then define some sample health data that we want to translate. Next, we initialize the T5 model and tokenizer specifically for translation tasks through the health data. We iterate through the health data, translating each entry using the T5 model. The translated text is then append to a list of further use. Finally, we print out the translated text for each entry, displaying the results of our translation process. This approach allows us to efficiently translate health data using the T5 model. This is the example how we implemented the code explained in the previous slide. Now coming to the outputs. You can see that the outputs from the multilingual forms using both the MarianMT and T5 models. For MarianMT model, we input the language abbreviation DA for Danish, and it translated the medical forms details into Danish accurately. This included translating fields like name, age, height, weight, and medical conditions. On the other hand, the T5 model successfully translated medical forms into French with details such as names and illness. Both models basically demonstrated high accuracy in their translations, showcasing their effectiveness in handling multilingual medical forms. Now, comparing the T5 model and MarianMT model, first in terms of accuracy, MarianMT model outperformed T5 model, achieving a slightly higher percentage of correct translations. Regarding process speed, MarianMT also has an edge over T5 model, which edge over T5 model and handling translation faster than T5, which is crucial for applications where speed is essential. However, T5 demonstrated superior contextual understanding, delivering better translations for complex sentences and nuanced context. This makes the T5 particularly strong in handling uh, intricate language tasks, while MarianMT excels in speed and overall accuracy. Now, the key benefits of generative AI in translation is that first, these models is significantly enhance the translation accuracy, ensuring that the output is precise, reliable, which accounts for 30% of the value. They also improve user accessibility by offering intuitive multilingual interface, making it easier for users to interact in their preferred language. This is 25% of the benefit. Generative AI models also adapt at maintaining cultural sensitivity, considering the nuances of different cultures for effective communication, which contributes 20% of the value. Another advantage is real-time translation, which eliminates delays and enables seamless instant communication across languages, covering 15% of the benefit. Lastly, these models are highly scalable. Lastly, these models are highly scalable, able to handle increasing translation demands while maintaining consistent performance, representing 10% of their overall benefit. In conclusion, our research highlights the significant impact of generative AI, particularly through the MarianMT and T5 models, in enhancing multilingual communication by breaking down language barriers. While pre-trained models have shown impressive effectiveness, they often require fine-tuning to perform optimally in specific domains. Future development will depend on ongoing research, innovation, innovative architectures, and the creation of domain-specific data sets to further improve translation quality and adaptability. Collaboration between scholars and the industry stakeholders will be essential to drive these advancements and address the evolving needs in multilingual communication. Looking ahead, the future scope of our research paper is first, we aim to improve data collection methodologies to reduce biases and ensure our data sets are diverse and representative. We will explore advanced AI models like GPT-4 and BART to enhance multilingual forms translation capabilities. And fine-tuning these models with domain-specific data set will also be a priority, particularly for sectors like healthcare and law to boost translation accuracy. Additionally, we plan to expand and support for less common languages and dialects by developing or adapting new models. We are also interested in integrating multi-model translation, such as combining text with visual information to improve cross-language communication. Finally, we will address challenges including accuracy, cultural sensitivity, resource demands, and ethical considerations. Thank you.